Yes. Okay, here the radio link control here also in the RLC, which is an important sublayer and which carries more a lot of informations. Remember that ARQ or is used for RLC is different from the hybrid IRQ used at physical layer or layer 1, as explained before. So the main differences are depicted on the slide. So the HARC functionality ensures delivery between peer entities at physical layer. So in NR or new radio, HARC or hybrid automatic request provides fast retransmission on physical layer and is controlled by MAC, as explained here. We have the MAC or the medium access control. The main functions of medium access control are specified in 3GPP terms, which is mentioned here, and it's used for multiplexes, logical channels, and perform HARC and handle carrier aggregation as well as managing scheduling. In this part, the main service and functions of the MAC sublayer are illustrated here as be explained. So in 5G NR, MAC supports multiple numerologies and multiple MAC SDUs from the same logical channel without concatenation in RLC. So it needs more time to explain all the details here, but at least we give an overview about the sublayer and what it consists and how we can and how it is used in our case. The RRC or the radio resource control here. So the radio protocols we were talking about in the previous slides are present in both user and control planes. Yes, so the radio resource control or RRC is used in the control plane only in the control plane. So this protocol is specified in 3GPP. So technical specifications as mentioned here in 3GPP with the first version in December 2017 and March 2018. So full standalone 5G RRC in June 2018, as mentioned by 3GPP, will be present. So the RRC takes care of the system information broadcast, connection establishment, connection control, mobility, and measurement. So further RRC in 5G NR supports on-demand system information provision. Here also for the RRC, we have multiple states in RRC. We have RRC in inactive states is a state introduced in NR for power saving purposes. So it means the UE or the handset is in RRC inactive states, and in this case it will not make exchanges with the network, so it will save its battery life. So latency reduction compared to idle is achieved by keeping UE context in RAN or radio access network. So measurement requirements are relaxed compared to connected mode here. Also here the system information handling, we have two terms, the minimum SI and other SI. Here the NG interface supports a one-to-many relation between NG RAN and the nodes. Yes, here. The NG user interface or NGU is defined between the NG RAN nodes and the UPF. The transport network layer is built on IP transport and GTPU is used on the top of UDP IP here. So those are the NGU protocol stack. We have the NGU provides non-guaranteed delivery of user plane PDUs between the NGRAN and the UPF. Here in this slide, so the interface allowing to interconnect two G node Bs or one G node B and one NG node B with each other is referred to as XN interface. We have here XN interface. Yes, we have the XN user plane or XNU, and we have the XNC or XN control plane. The XNU is the so this interface is defined between the NGRAN nodes, between the antennas. Yes, so the transport network layer is built on IP transport, and GTPU is used on top of UDP IP to carry the user plane PDUs. We have here the XNC or the XN control plane interfaces. It is defined between the two NGRAN nodes. So the transport network layer is built on SCTP on top of IP here, as mentioned here. So we have the XNU protocol stack. Here, how to read it. And we have the XNC or control plane protocol stack. So the SCTP layer provides the guaranteed delivery of application layer messages. So in the IP layer, point-to-point transmission is used to deliver the signaling PDU. Here, in this chapter, we will talk about the 5G spectrum. So we expect that at the end of these slides, you will be able to describe what is the 5G spectrum. Excuse me. You should be able to describe what is the 5G spectrum used to identify 5G operating frequency bands, and to explain supplementary uplink and least supported NR bandwidth. Here in this table, we have our division of 5G spectrum. Please to refer to this page here to see that there is a relation between the cell range and the data rates. So when the cell range go low, the data rates go high. I will explain. 5G is the first ever radio system that is designed to support any spectrum between 400 megahertz and 90 gigahertz. So 3GPP has decided that NR or new radio, which is 5G, will from release 15, as explained before, support operation from below 1 gigahertz up to 52.6 gigahertz, as well as operation in both licensed and unlicensed spectrum. As you know, we have the licensed spectrum and we have the unlicensed spectrum. So the wide range of spectrum operations are needed to provide the optimal combination of high capacity, high data rates, and the coverage and ultra high reliability. So low bands below 6 gigahertz are useful for wide area coverage and data rates up to a few gigabits per second. Reliable coverage is an important factor in providing connectivity solution for Internet of Things. Reliable coverage is an important factor in providing connectivity solution for Internet of Things devices and for critical machine communication like remote control or automotive communication. So 5G at mid bands around 3.5 gigahertz, which is the spectrum used by the majority of the operators in the world for 2 days. So in this band, it can utilize existing base station sites by providing similar coverage as the existing LTE network at 1.8 gigahertz. So we are almost in the same range from 1.8 gigahertz, which is used by our LTE networks, and the new spectrum used by the majority of the operators in the world in today, which is 3.5 gigahertz. So it gives similarly the same coverage. So millimeter waves have several bands available to provide, which means it will provide a huge capacity and throughput. They are optimized for extremely high data rates for local hotspots or for fixed wireless connections. However, higher frequencies are also associated with higher radio channel attenuation, so limiting the network coverage. There is a relation. So when going to the millimeter waves beyond the 20 gigahertz, from 25 to the 52 gigahertz, so there will be a channel attenuation and it will be limiting the network coverage. Although this can partially be compensated by the mean of 5G beamforming, which is an important term and topic which will be discussed later. So the 5G beamforming, in a mean, it will compensate the limit of the network coverage caused by the using of millimeter waves, which are the high frequencies for more than 20 gigahertz. Here we have the main 5G spectrum options in different markets globally. We have here the Great Britain, we have Canada, Europe, United States as the first, we have Germany, and we have Korea, we have China, for example. So around the world, the bands given in this table have been allocated for targeted. So the main spectrum options globally for 5G in the early phase are at 3.3 to 4.9 gigahertz. And millimeter waves are from 24 to 28 gigahertz, and from 37 to 40 gigahertz, and 64 to 71 gigahertz. Here we have, or we use what we call the time division duplex, the TDD technology. So 5G can also, or can utilize also sub 1 gigahertz frequency division duplex, FDD. So when using the frequencies lower than 1 gigahertz, we use what we call the techniques, the FDD, or the frequency division duplex bands, to provide wide area coverage, including deep indoor penetration. So low band spectrum can be 700 megahertz or 600 megahertz, which is lower than 1 gigahertz, which it could be 850 or 900 megahertz refarming. So by minimizing the usage of legacy 2G and 3G spectrum, the aggregation of the different spectrum bands from sub 1 gigahertz to millimeter waves will give the optimal combination of coverage. This is the case, and this is the most important used techniques in getting more spectrum and more capacity and more data rates. 5G can be deployed also on shared spectrum, like 3.5 gigahertz band in USA, and in unlicensed spectrum like 5G, like here. It is used in the USA. So that approach opens new possibilities for enterprises and industries to take benefits of 5G technology without spectrum license. Okay, here we have the spectrum availability. So 5G networks are expected to operate over a wide range of licensed and unlicensed frequencies in low, medium, and high spectrum bands. But those frequencies have yet to be specified specified or specifically defined by 3GPP. As mentioned in the previous slide, it can be assumed that most of the bands currently being used for 2G, 3G, and 4G networks will be reallocated in time to 5G technologies. Last but not least, globally harmonized spectrum remains integral to the continued growth of the mobile industry and should be touchstone for selecting spectrum for 5G new radio. Here we have the 5G NR or new radio operating frequency band. We have the definition of frequency range. Just to keep in mind that we have two frequency range, the FR1 or frequency 1 and the FR2, which is frequency 2. There are two ranges. The first one is from 450 megahertz to 6 gigahertz or 6,000 megahertz. We have the second frequency, which is the second frequency range, which is FR2, which is from 24 gigahertz to 52.6 gigahertz. So the frequency ranges in which, excuse me, the frequency ranges in which NR can operate in release 15 are identified as depicted in the table on the slide. So two types, we have FR1, we have FR2. So depending on the ranges, the maximum bandwidth and subcarrier spacing varies. We have the carrier spacing, which is a term used in 5G planning and optimization. So depending on these ranges, the maximum bandwidth and subcarrier spacing varies. In FR1 or frequency 1 ranges, the maximum bandwidth is 100 megahertz. And in FR2 or frequency 2 ranges, the maximum bandwidth is 400 megahertz. For example, as we are here in our live networks, I'm working now on an LTE and VoLTE project. We have the maximum of 100 megahertz of after aggregating multiple bands. So this is the maximum used. We are now at FR1. So imagine with me if we pass to FR2 in 5G. We can here, when we are using 100 megahertz as a bandwidth, we can reach till to 1.5 approximately gigabit per second as throughput. So imagine we have a 400 megahertz in FR2 for the 5G cases and with the new technology. So the throughput will be very high, more than 20 gigabit per second per user. So, as I said, we are at 100 megahertz for FR1 and 400 megahertz for FR2 when using this range. Here we can see that the 5G NR operating bands are divided according to FR1 and FR2 for both uplink and downlink, and the technologies used if it is TDD or FDD. So we can ask the question, what are the frequencies bands supported by 5G NR? So remember, an operating band is the frequency range in which NR operates, paired or unpaired. What we mean by paired or unpaired, it means the FDD or TDD. So that is defined in a specific set of technical requirements. So the specified frequency band of 5G NR as per 3GPP release 15 are listed in this table here. In accordance with the spectrum requirements defined by another report of 3GPP. So as you can see from this table, NR has introduced a new notation for band which starts with N here, N1, N2 to N66. So band 20, for instance, is noted, for example, N20. Yes, where in LTE it was termed as B20, for example, which is band 20. So furthermore, apart from frequency ranges NR, bands can be classified into 3 categories. We have the frequency division duplex band, or FDD, as mentioned here. We have the time division duplex band, or the TDD, as mentioned here. We have the supplementary bands, supplementary downlink, SDL, as mentioned here, and supplementary uplink, SUL, as mentioned here. So this is a table defined by 3GPP, and you can refer to it anytime you are documenting or planning or need some other informations in your coming projects. We have here the SUL and SDL. Yes, the supplementary downlink and the supplementary uplink. The supplementary downlink or uplink allow the bounding of unpaired spectrum with FDD or TDD bands. I repeat, the supplementary downlink or uplink allow the bounding of unpaired spectrum with FDD or TDD bands. So to significantly enhance NR network or new radio 5G network capacity and users' experience. So this provides an efficient way of using spectrum because consumption, rich content, and other data heavy applications is asymmetric. It is a detailed information and detailed explanation. It needs more time, but I will just additionally to improve uplink coverage for high frequency scenarios. Supplementary uplink or SUL can be configured as shown in the slide. So with SUL, the UE is configured with 2 uplink for 1 downlink of the same cell as depicted on the slide. Here, I know it's a detailed information. It needs to be explained maybe in other lessons. So this is just for planning and optimization. We have here the NR channel bandwidth. So the definition of channel bandwidth and retransmission bandwidth configuration for one NR channel is depicted in this chart. So the base station channel bandwidth supports a single NR RF, or radio frequency carrier, in the uplink and downlink, as mentioned. So it is measured in megahertz and is used as a reference for transmitter and receiver RF requirements. We have here the supported NR channels. NR is new radio and it is the 5G. So the supported NR carriers bandwidth and transmission bandwidth configuration are mentioned here in this table. We have the FR1 and the FR2 according to the 2 ranges. So the transmission bandwidth configuration for each base station channel and subcarrier spacing is specified in these 2 tables for frequency ranges FR1 and FR2. Remember, as mentioned previously, multiple component carrier can be aggregated to achieve up to 6.4 gigahertz of transmission bandwidth. This is the power of 5G. The maximum bandwidth that we can achieve in our today networks is 100 megahertz as a maximum. So imagine in 5G, by using multiple frequencies bands from FR1 and FR2, and for each frequency, not the frequency range, but the frequency, we can get up to 400 megahertz. And after aggregation, we can get up to 6.4 gigahertz of transmission bandwidth. It's a huge bandwidth, and it will it will solve a lot of problems. It will enhance our daily lives. It will be very efficient for the use cases coming for the 5G, for the IoT, for the automotive, for the self-driving, for the remote surgery, for everything. So it will solve a lot of problems. I really want everybody to concentrate on the use cases of the 5G and try to get more knowledge and more skills, because really it is the future. It is the future. Here we have the NR-ARFCN. This is a parameter for the global frequency raster. So this is one of the parameters used for planning and optimization. So as I said, the channel raster or raster defines a set of RF reference frequencies that are used to identify the RF channel position. This is one of the detailed topics here. So to conclude, it is worth noting that NR or 5G supports flexible spectrum use through mechanism including the following. So multiple component carriers can be aggregated to achieve up to 6.4 gigahertz of transmission bandwidth. This is huge. The 5G supports spectrum sharing with LTE, so it can use the frequencies or share the same frequencies with LTE. The operating carrier of 5G and LTE can be overlapped or adjacent. Lastly, 5G addresses the uplink and downlink traffic asymmetry with flexible spectrum resource allocation by allowing FDD operating on a paired spectrum, which is TDD. So as a conclusion on the 5G technology, and I found it on studies, so a study from the site Hindawi tell that 5G will be able to sustainably satisfy the requirement for 1,000-time traffic growth. So 5G will provide users with fiber-like access data rates and zero latency user experience. So 5G will be capable of connecting 1 billion devices, 100 devices. So 5G will be able to deliver a consistent experience across a variety of scenarios, including the cases of ultra-high traffic and volume density and ultra-high connection density and ultra-high mobility. So 5G will also be able to provide intelligent optimization based on services and users awareness, and will improve energy and cost efficiency by over 100 of times. So enabling us all to rely the vision of 5G, information a finger away, everything in touch. Thank you for listening, and this is the end of the webinar. Thank you.